What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 3, Section 6, Absolute Value Functions. Let's do it. So how do you solve an absolute value equation? So in general, right, let's say we have 3 plus the absolute value of x is equal to 7. So the first thing you're going to do is you're going to isolate whatever is in the absolute value bar. So I'm going to subtract 3, and then we're going to have absolute value of x equals 4. Then we're going to split this into two equations, okay? The first equation is just as is. We remove the absolute value symbol, but we leave the number. For the second equation, we still remove the absolute value, but then we flip the sign of the number on the right-hand side, so it's -4. Now, in this case, we've gotten our answer, which is +4 and -4. And if you plug it back into the original equation, you'll see it works. The absolute value of 4 is 4 plus 3 is 7. The absolute value of -4 is 4 plus 3 is also 7. Boom, done. When solving an absolute value function, the isolated absolute value term is equal to a negative number. What does that tell you about the graph of the absolute value function? So what this means is, let's say we have a function f of x equals the absolute value of x plus 7. Now, if we were to plug 0 in for f of x, right, and then solve for x, what would happen is we'd have 0 equals the absolute value of x plus 7. Then we'd subtract 7 from both sides. Absolute value of x equals -7. So what we've done is we plugged in 0 for the function. We've solved for the absolute value. Now, we know that an absolute value is always going to be positive. It's the positive purifier. So in this case, saying absolute value of x equals a negative number, that's not going to happen. There's not going to be a solution that is going to be possible for the value of x here. So what this tells you about the graph, the original graph of f of x equals absolute value of x plus 7, is that it has no x-intercepts. There's no points at which this function will ever equal 0. So that means it's either above or below the x-axis, never intersects it. Boom, done. Describe all numbers x that are a distance of 4 from the number 8. Express this set of numbers using absolute value notation. So when we're talking about distance, it's almost the same as the word difference if we're talking about absolute value. So we want things that are a distance or a difference of 4 from the number 8. So how do we get the actual distance of 8? Well, I take my number x, whatever it may be, and I subtract 8. Now, when we talk about distance, that is a positive number, right? So even if that number is, if x is like, let's say 7, we'd say 7 minus 8 is -1, but it's still 1 away from 8. So I throw this in absolute value. That gives me the distance from 8. We're saying we want this distance to equal exactly 4. So what I'm going to do is I'm going to set this equal to 4, and now I have an absolute value equation that I can solve. So check this out. We're going to split it first. First thing I'm going to have x minus 8 equals +4. Then I'm going to have x minus 8 equals -4. We keep this the same, but then we negate that answer. And then we're going to isolate by adding 8. Boom. We got x equals 12. And then I'm going to add 8 here and here. We've got x equals 4. And so these are the two numbers that are 4 away from 8. It's 4 and 12. Boom. Done. Describe the situation in which the distance that point x is from 10 is at least 15 units. Express the set of numbers using absolute value notation. So once again, we're talking about distance from a point. So the distance is from x from 10 is at least 15 units. So the distance between x and 10 is, again, the difference, but then we throw that in absolute value. Now, when they say at least 15 units, now we're not talking about an equation anymore. We're talking about an inequality, and at least is the same as greater than or equal to 15. There's your inequality. Boom, done. So for this one, in order to find the x-intercepts, we're going to set the function value to 0 and solve for x. So check this out. So first I'm going to subtract 4 from both sides. Then we're going to divide by 4 like so. And that gives me -1 equals the absolute value of x minus 3. Now, when you have this point, right, absolute value of something equals a negative number, there's not going to be a solution because absolute value is always going to be either 0 or a positive number. So that means there are no x-intercepts. For the y-intercept, all we're going to do is plug 0 in for x. So it's 4 times the absolute value of 0 minus 3 plus 4. 0 minus 3 is -3. Absolute value of that is +3, right? Absolute value purifies or makes the number positive. And then 4 times 3 is 12 plus 4 gives us 16. So my y-intercept is going to be 0, 16. Boom, done. So for this one, first we're going to find the x-intercepts, and the x-intercepts are going to exist when the function value is 0. So I'm going to plug in 0 first for f of x. Then I'm going to subtract 6 from both sides. Then I'm going to divide both sides by -2 like so, and then we get 3 equals the absolute value of x plus 1. And now we're going to split this, okay? We're going to say first -3 equals x plus 1, just stripping away the absolute value, that's the negative. And then the positive side, x plus 1 just equals regular 3. And then we're going to solve by subtracting 1 from both sides. Is going to be x equals -4. Boom, like so. And this one, subtract 1 from both sides. This one's going to be x equals 2, like so, which means my x-intercepts, I'll put that up here, my x-intercepts are going to be -4, 0, and 2, 0. In terms of the y-intercept, I'm going to plug in 0 for x and evaluate. So 0 plus 1 is 1 times -2 is -2 plus 6 is 4. So my y-intercept is, again, when x equals 0, y in this case will be 4. Boom, done. For this one, to find the x-intercepts, again, I'm going to plug 0 in for the function value. Then we're going to isolate by adding 6 to both sides. Then we're going to divide by 2. And now we're going to bifurcate. We're going to split this into two equations. So first, I'm going to leave it as is. Regular 3 equals x minus 1 with the absolute value gone. Then we're going to have the negation of that 3, -3, also equaling x minus 1. We're going to add 1 to both sides. Here we get 4. Here we're going to add 1 to both sides, and we get -2. So my x-intercepts, therefore, are going to be 4, 0, and -2, 0. Now to get the y-intercept, we plug 0 in for x. So 2 times absolute value of 0 minus 1 minus 6. 0 minus 1 is -1. Absolute value of that is 1 times 2 is just 2. Minus 6 is -4. So my y-intercepts are going to be 0, -4. Boom, done. For this one, to find the x-intercepts, we're going to plug 0 in for the function value and solve for x. So first, I'm going to subtract 16 from both sides. Then I'm going to divide by -1 to get rid of that negative, and then 16 equals the absolute value of x minus 9. Now we're going to split this into two equations. First, it's just 16 as is equals x minus 9 with the absolute values removed. And then here again, we're going to remove the absolute value bars, but we're going to negate that side to make it -16. Now we're going to solve for x. So adding 9 to both sides, we get 25, and same thing here. We get -16 plus 9 is -7. So my x-intercepts, therefore, are -7, 0, and 25, 0. And now here for the y-intercept, we're going to plug 0 in for x, and we've got 0 minus 9 in absolute value plus 16. That would be -9. Absolute value that is +9, but then we have the negative out front. So again, it's -9 plus 16, which is 7. So the y-intercept is 0, 7. Boom, done. So when we graph an absolute value function, it's important to know where the vertex is, where that point is at the bottom. So we can figure that out by figuring out what's going to zero out my inside of the absolute value bars. And that's going to be when x is -1. So this is a really good starting point. Whether this goes up or down, we know that the point, that bottom corner is going to be at when x equals -1. Let's get the corresponding y value, plug it in. -1 plus 1 is 0, so y is 0. So here's that original point. Now we can choose points to the left and right of -1 to complete the graph. So I'm going to choose -2 and -3. I'm also going to choose 0 and 1. So plug in -2 in. -2 plus 1 is -1. Absolute value of that is +1. -3 plus 1 is -2. Absolute value of that is +2. Plugging in 0. 0 plus 1 is 1. Absolute value of that is 1. And 1 plus 1 is 2. Absolute value of 2 is just 2. So now we have 5 nice points, right? We can do 0, 1, and we can do 1, 2. We can also do -2, 1, and -3, 2. And then there I just connected the dots. There's your absolute value function graph. Done. So for this one, I'm going to show you two different ways that you can graph this. The first is you can kind of look at this like being in vertex form. So for example, there's nothing in that absolute value. So I know that my point of the vertex is going to occur when this zeroes out, meaning when x is 0 in particular. And when x is 0, you see that you get a function value of -2 for y. So I know that I'm at 0, -2 for my vertex. And then, so this is just absolute value of x. There's no multiplier, no nothing. We're left with our typical slope of +1 to the right of this, -1 to the left. So without doing too much work, we've got a nice absolute value graph. But now let's talk about that 5-point method as well, which is another perfectly fine method to use. So we started off with that nice vertex. And once again, just as a reminder, we got the vertex by figuring out when this absolute value expression is going to zero out. It's going to be when x equals 0. So we have our middle point. Then we can get a couple points to the right, 1 and 2, and to the left, -1, -2. You plug in 1, absolute value of 1 is 1, minus 2 is -1. Plug in 2, absolute value of 2 is 2, minus 2 is 0. Same with -1, right? -1, absolute value that is 1, minus 2 is -1. Plug in -2, absolute value that is 2, minus 2 is 0. And check it out. Here are the points that we just calculated. 1, -1, 2, 0, -1, -1, -2, 0, boom, done. So for this one, once again, the vertex is going to be when the x zeroes out, and that's going to be at 0. You plug in 0, you get -2 for y. So we know we're at 0, -2 for that nice vertex. Now, when we want to graph this, we can look and say, kind of like thinking about what's the slope for a linear equation, right? What's that value in front of x? Well, it's -1, okay? Because there's a negative there, which means to the right, it's going to have a negative slope. To the left, it's going to have a slope of +1. And that's that. So there's our graph. Again, going back to that nice 5-point method, let's start with the vertex at 0, -2, and then we're going to go -1, -2 to the left, 1, 2 to the right. So I plug in -1, that's 1 with a negative is -1, minus 2 is -3. Plug in -2, that becomes +2 with the negative becomes -2, minus 2 is -4. Over here with the 1, that becomes 1 with the negative. -1 minus 2 is -3. Plug in 2, absolute value of 2 is just 2, with the negative is -2, minus 2 is -4. Look at these points, right? -1, comma, -3 right there, and then -2, -4 right there. And then here we have 1, -3, and 2, -4. So it all matches up, boom, done. So for this one, we're going to start off like the other ones. We're going to start by finding that vertex, aka when this is going to zero out. It zeroes out when x equals 1, because 1 minus 1 is 0. So we know we have the vertex at 1, comma, plug in 1, that's 0. -0 minus 2 is just -2. So there's our vertex at 1, -2. And then again, we can look at that quote-unquote slope, this coefficient in front of the absolute value, and it's a -1. So this means from the right, we have a slope of -1 like so, and then to the left, we have the opposite, a slope of +1, boom, done. Now to verify with the 5-point method, we are going to start at the vertex, which is 1, -2, and we're going to build around that. Go to the left by 2, 0, -1, to the right by 2, 2, and 3, and plug and chug. Plug 0 in, 0 minus 1 is -1, absolute value is +1, negate it, -1 again, minus 2 is -3. This one, -1 minus 1 is -2, becomes +2, then negate it to -2, and that's -4. And then these values are going to be much the same. You can plug them in for fun and check, but it's going to be a mirror of what we see here and here. So now we see that point 0, -3, -1, -4, 2, -3, 3, -4, boom, done. So when we're trying to graph this function, we're going to first start with that vertex point. We're going to figure that out by knowing what is going to zero out what's inside the absolute value, and that's going to be -3. And to find the y value of the vertex, we're going to plug and chug. So -3 plus 3 is 0, times 2 is 0, plus 1 is 1. So now we have the vertex at -3, +1. And this is like the slope to the right. So we have a slope of +2 to the right. And then on the left side, it's that slope but negated. So a slope of -2 to the left. And there's your graph. And now we're going to verify with the 5-point method, starting with the vertex at the center, and then going down 1, down 2, up 1, up 2. So plugging in -2, -2 plus 3 is 1, times 2 is 2, plus 1 is 3. Plugging in -1, -1 plus 3 is 2, times 2 is 4, plus 1 is 5. And then on the flip side, -4 plus 3 is -1. Absolute value of -1 is 1, times 2 is 2, plus 1 is 3. And notice how these mirror. These are going to be the same as well because of that nice symmetry around the vertex. So this is going to be 5. And then here are the points. -1, 5, negative 2, 3, negative 4, 3, negative 5, 5, boom, done. So here we're going to start by zeroing out that inside part once again. What value of x is going to make that go to 0? That's going to be 2, right? 2 times 2 is 4, minus 4 is 0. And then the y value will be that negative 3 because you have 0 minus 3, negative 3. There's your vertex. Now, normally I'd say the slope is this invisible value out front, but here this coefficient kind of changes things, right? So it's not going to be that nice slope of 1 and negative 1 to the right and left. So we're going to use the grid method once again. So when I plug in 3, I get 3 times 2 is 6, minus 4 is 2. 2 minus 3 is negative 1. Plug in 4. I get 2 times 4 is 8, minus 4 is 4, minus 3 is positive 1. So we have positive 3, negative 1, positive 4, positive 1. And then to the left, plug in 1. You get 2 minus 4 is negative 2, absolute value of that is positive 2, minus 3 is negative 1. So there's our negative 1. And plug in 0, we get 0 minus 4 is negative 4. Absolute value of that is positive 4, minus 3 is positive 1. And there's our y-intercept. And now connecting the dots, we get our final graph. Boom, done. For this one, we're going to start off with the vertex, aka when is this going to zero out? That's when x equals 1. And then you plug in 1. 1 minus 1 is 0. Negative 0 is just 0. Minus 3 is negative 3, and there's our vertex, 1, negative 3. Now again, I see a negative 1 in front here, and that's going to act like the slope to the right. So we're going down like that, and then the negation of that to the left, which is positive 1, and there is our graph. Now we're going to verify with the 5-point method. We're going to plug in 2. 2 minus 1 is 1. That's negated is negative 1. Minus 3 is negative 4. Plug in 3 minus 1 is 2. Absolute value of 2 is 2. Negated is negative 2. Minus 3 is negative 5. And again, we have that nice symmetry, so we know this is going to also be negative 4, but you can plug and chug just to make sure. And this is going to be negative 5 up top. And these points here match up. 2, negative 4. Boom. 3, negative 5. Boom. 0, negative 4, negative 1, negative 5. Boom. Done. Once again, to find the vertex, we're going to figure out what x value is going to zero out the absolute value, and that's going to be negative 4. And then you plug that in, this zeroes out. You get a y value of negative 3. So that's the vertex, negative 4, negative 3, boom. Now, once again, we got nothing in front of the x, so this coefficient here is going to dictate the slope to the right, which is 1 over 2. So to the right, it's going to look like this. To the left, it's going to be negative 1/2. Which is going to look like this, boom, done. Now we're going to use the 5-point method again, but instead of going up by 1 and down by 1, I'm choosing to go up and down by 2. And this is just out of convenience to make it easier because I'm multiplying by 1/2. So if I always have a multiple of 2 that I'm evaluating and multiplying times 1/2, I'm going to get nice whole numbers. It's going to be easier. So check this out. Negative 2 plus 4 is 2 times 1/2 is 1 minus 3 is negative 2. 0 plus 4 is 4 times 1/2 is 2 minus 3 is negative 1. So we get those nice whole number values. Likewise, negative 6 plus 4 is negative 2. Absolute value of that is positive 2 times 1/2 is 1 minus 3, negative 2. And again, it's going to be negative 1. That's all going back to those nice symmetry properties based around the vertex. And you can see this point, negative 2, negative 2, 0, negative 1. Negative 6, negative 2, negative 8, negative 1, boom, done. Use a graphing utility to graph f of x on the viewing window negative 5 to 5. And those are x values, right? It's really a domain. So we're going to use Desmos, and then we're going to identify the range. So what I've done in Desmos is I've put in the function here, negative 100, absolute value of x plus 100. And then I specified the domain to go from negative 5 to 5. So it's only showing the graph for those x values. Then I adjusted the viewing window for the range to make sure to get all the values to get the full graph in the picture. And what you can see is this function is as low as negative 400 for negative 5 and positive 5. And it goes up to this high point of 0, 100, which means the range is from negative 400 to positive 100. So we're going to write that out with square brackets because we're including negative 400. We're including positive 100. There is the range, boom, done. For this one, we're meant to graph on a graphing calculator, so we're going to do that now. And then we're trying to get an appropriate window so you can see the entire function, or the critical points of the function, I should say. So let's do that now. So when we look at this function, it kind of fits that standard prototype and that standard form that we've been seeing where it's x minus something, and that something, because we're trying to zero out the absolute value. So the value, that's something that we're subtracting, is actually the x value of the vertex. So that's helpful because this thing doesn't even go up to 5 times 10 to the 9th. By the way, 5 times 10 to the 9th is 5 billion. It's a big number. Also, we see that the vertex is going to be for the y value at 2 times 10 to the 9th. Because if we plug in 5 times 10 to the 9th, this whole part's going to zero out and we're going to get that. So at a minimum, to include the vertex, we have to adjust and expand the window to get to these values. So I played around with the viewing window to kind of get a full view of the V and the vertex and everything. And we really need an expansive viewing window. Now, again, we knew that the vertex was going to occur at 5 times 10 to the 9th, 2 times 10 to the 9th. So that shows up there. This y-intercept we didn't know, but it ends up being 2 times 10 to the 19th. So as you expand it vertically to get that y-intercept, now we got a pretty good view. And then we also got this, the right side of the function going up to 1 times 10 to the 10th. So this is a pretty sufficient viewing window. You get a nice view, and you have to really zoom out because these numbers are so big, but that's how you do it. Boom, done. So for this question, we're asked to find a value of a such that there are no y-intercepts. But the thing is that this is going to look like a v no matter what, with kind of a slope of 2 going to the right, -2 going to the left. And the vertex is going to be at -1, a, whatever that a value is. Well, this means that this side is always going to hit the y-axis at some point. All that a is going to change is the vertical placement of the vertex, moving it up or down. But it will always have a y-intercept, so there are no values that will get rid of the y-intercepts. Boom, done. The true proportion P of people who give a favorable rating to Congress is 8% with a margin of error of 1.5%. Describe using an absolute value equation. So when we talk about margin of error, what we're saying is when it says 8%, it means we are within 1.5 in either direction, meaning this could be as high as 9.5% or as low as 6.5%. Now, to represent this in an absolute value equation, the way we do it is we say our true proportion P, and then we're trying to see like how far are we from this actual number of 8%. So it's again the distance, aka the difference. So we're going to subtract it, and I'm going to put this into decimal format. So that distance from 8% is going to be within or less than or equal to 1.5%. Again, in this format of decimal format 0.015, and there is your absolute value inequality. Boom, done. A machinist must produce a bearing that is within 0.01 inches of the correct diameter of 5 inches. Using x as the diameter of the bearing, write the statement using absolute value notation. So for this one, we're trying to get within 0.01 inches of that 5 inches. So we want the distance from 5, aka the difference with 5, to be less than or equal to 0.01. So we can set it up kind of similarly as we've done before. So we want x, which is the diameter. We want the difference or the distance from 5 to be less than or equal to 0.01. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.